So this is from the 2002 AP Calculus AB exam. This is problem number 5. It's a non-calculator question. And basically the setup is we have this cone, and the cone has water in it, and the water in the cone is evaporating. We know the dimensions of the cone. We have a diameter of 10 across the top, height of 10, and we also are told in the problem setup here that the water in the container is evaporating so that its depth h is changing at this rate, -0.3 centimeters per hour. They were nice enough to provide us with this volume formula here for the volume of the amount of water in the cone. And what we're asked to do in part A is we're asked to find the volume of water in the container when the height of the water is 5 centimeters. So that should be easy enough. There's not really any calculus involved in part A. It wants to know what the volume of the water is when h is 5. So if we think about this, when h is 5, obviously we're just going to put 5 in place of the h here. We don't really know what r is when h is 5. So what I want to do is I want to do some geometry right now that's going to come in useful whenever we answer the other parts of this question in a few minutes. So if I try to draw a two-dimensional side view of the cone, it's basically just going to look triangular in shape, right? So here is a two-dimensional side view. And what we know is we know that the height of the entire cone is 10 centimeters, and we know that the diameter across the top is 10 centimeters as well. So what we want to determine is when the cone has 5 centimeters of water in it, so when the height of the cone is 5, so this dimension would be 5 centimeters. We want to know the volume, so what we're going to have to determine is we're going to have to determine what this radius of the amount of water in the cone is at that time. And so if I kind of extend this upward, and that is not a very good diagram here, but I think it'll do what we need it to do. We know that the diameter across the top of the cone was 10 centimeters, and although my diagram doesn't really indicate this, this would have to bisect the top of the cone. And so this would be 5 centimeters here, and this would be 5 centimeters more the rest of the way from the center over to the other edge of the cone. And so the reason why I'm doing this is because if you think about just this piece of the diagram, and I guess I can try to redraw this again. If you think about just this piece of the diagram, what you basically have are two similar triangles. If this is r, and we're looking for that r, and this is 5, and you know that this entire height is 10, and this dimension right here is 5, right, the height at the instant in time we want to know something at, you can use similar triangles to figure out what r is. And so the relationship between the corresponding sides here would be that this dimension on the big triangle is 10 centimeters. Take the ratio of that to the dimension across the top of the big triangle, which is 5 centimeters, right? So I have 10 centimeters to 5 centimeters. That has to be equal to the side that corresponds to the 10 centimeter side on the big triangle, which would be 5 centimeters on the little triangle over the side that we don't know, r. And so what we can go ahead and do here is we can go ahead and cross multiply and solve. And so when we cross multiply, we're going to get 10r equals 25. And so r is going to have to end up being 25 over 10, which would be 2.5. So r is going to have to be 2.5, which as a fraction, of course, would be equal to 5 halves. And so what is the volume of the amount of water in the cone or in the container when the height is 5? Well, now what we know is the radius at that instant. So now it's just a matter of using this formula to go ahead and evaluate for our volume. So our volume is going to end up being equal to 1/3 times pi. So I'm just applying the formula that they gave us, times r squared, and for r we got 5 halves, times h, and the height at this instant was 5 centimeters. Now I know I didn't really include any units here, but think about them real fast. This is dimensionless, it's a constant from right here, as is pi. This 5 halves is measured in centimeters, so when we square that we get centimeters squared. 5 is also measured in centimeters, so the units of volume would be in cubic centimeters, and then it would just be a matter of simplifying this a little bit. And so let's see, if we did 1 times pi times 25 times 5 more, that's going to give us 125 pi. Right, so I basically just did top times top of this fraction times, well, I had to square the top of this fraction, that's where the 25 came from, and then times this extra 5. So that gave me 125 times pi in the numerator. And then if we do bottom times bottom times bottom times bottom, it's going to be 3 times 1. 2 squared is 4. So 3 times 1 times 4 times 1 is going to give us 12. And then the units of that volume calculation are going to be cubic centimeters. So the volume of the water in the cone at the instant in time when the height is 5 centimeters is going to end up being 125 pi over 12 cubic centimeters.